So, now let us open the output file using ChemCraft and try to see how the UV visible spectra comes and look at the molecular orbitals also. So, the first thing, let us see the, you have to click single point geometry, go to the tools and show TD spectrum. You can see the CD spectrum by transition dipole moment or transition electric dipole moment or velocity dipole moment. I will just use the electric dipole moment. Now, you by doing this you can actually get what is called a stick spectra. So, you have to broaden it to match the experimental spectra. This broadening in experiment actually happens due to vibration. Orca has much better ways of take care of the vibrational averaging. You can look at the manual, but for most of the purposes it is fine to broaden the spectra using a Gaussian or Lorentzian distribution. And also it allows you to scale a particular axis to match the experimental spectra. It is often a good idea. So, what is generally done is that the lowest energy. So, this is given in wavelength. So, that means the lowest energy part is this one. So, the lowest energy part of the calculated spectra is shifted to match the lowest energy peak of the experimental spectra. This is a very common practice while trying to use calculated value for interpreting spectra. So, this is how the UV visible spectra looks like. Now, let us go to a molecular orbital. Going to the molecular orbital, let us see which molecular orbitals are actually important for us. So, we are going to only restrict our attention to first 4 of these state. It's more experimental values are available for more state, like it's I think for 8 states total the experimental values are available, and these are, remember, experimental values are actually can be of two kinds. One is a vertical excitation energy, one will be an adiabatic excitation energy. Vertical excitation energy means your excitation happens at the geometry of the ground state, and for the adiabatic excitation energy you need to take the energy difference for the energy of the ground state at that particular ground state geometry and energy of the excited state at the particular excited state geometry. So, you need to perform two separate calculation along with the geometry optimization for the excited state, and often there becomes a confusion between a vertical and adiabatic excitation energies. So, it is generally a good idea to go back to the original experimental reference and try to see what is actually reported. It is a vertical excitation energy or the adiabatic excitation energy which is written. So, we are going to keep our focus to first 4 states. So, my first state is gives me around 4.57, I should have written is 4.58 actually to make it a significant digit. This should have been 8.62, 9.48 is fine, 9.68 is also fine. And I have written the oscillator strength also. As we have discussed, the first state is a state where it is 0 oscillator strength, whereas this the second, third and fourth state has some oscillator strength. Now, you may ask the question, if the first state is actually of 0 oscillator strength, how people have observed it in the spectroscopy. Although it looks like as it is 0 oscillator strength, because of the molecular vibration, it can borrow some oscillator strength from other modes, and actually you can see it as a very low energy peak in the spectra. Now, if I look at the dominant transition, so in the first case the domination transition is 10, in the second case it is LUMO, plus 2, this one is LUMO plus 3, and this is again LUMO minus HOMO minus 1 to LUMO plus 2. So, we need HOMO minus 1, LUMO plus 1, LUMO plus 2, LUMO plus 3. So, let us go to render molecular orbital. you may get confused between these two outputs because Chemcraft start the counting from 1 and Orca started from 0. So, remember this is HOMO, HOMO minus 1, LUMO, LUMO plus 1, LUMO plus 2, LUMO plus 3. This is LUMO, LUMO plus 1, LUMO plus 2, LUMO plus 3. Do I need the LUMO plus 4? Let us see it again. No, for interpretation at least, if I restrict my attention to the dominant transition, I do not need the LUMO plus 4. It is LUMO, LUMO plus 1, LUMO plus 2 and LUMO plus 3. LUMO, LUMO plus 1, LUMO plus 2, LUMO plus 3. Okay. So, now all my molecular orbitals are there. Let us look at the first transition. It is HOMO to LUMO plus 2. So, let us see what is my HOMO. Oh, this is not the HOMO, this is the HOMO. Now, with this orbital says, see one thing, there is no node which is along the bond axis. That means this cannot be a pi bond, and if you look carefully, this actually looks like a p orbital. Sorry, it looks like a d orbital actually, it is a double dumbbell shape. So, this is actually one of these non-bonding orbital of H2CO, and so this is my donor orbital, and where the electron get excited is LUMO plus 2. So, here the ISO value is slightly higher, maybe I have to reduce it a little bit. Oh, I have to increase it a little bit, sorry. So, this is a pi antibonding kind of an orbital. So, this is an NP to pi antibonding kind of orbital. So, this is my first excited state. Now, let us look at my second excited state. So, the dominant transition is from HOMO to LUMO. The HOMO I have already seen, which is a non-pi. Now, I have to need to look at the LUMO. 0.6 was not the good one. So, now you see for this orbital, so the previous orbital, because it was it has an excitation from a valence orbital, from a n type valence bonding orbital, non-bonding orbital, it is not a bonding orbital actually, it should be called a non-bonding orbital to a pi type orbital. So, that was a valence excitation, whereas if you look at this one, this is an excitation which is actually goes from the HOMO to LUMO. And here you see a part of the orbital, this part is actually localized further away, and it looks a very diffuse kind of a orbital. So, these are like a Rydberg kind of a orbital. So, this is a Rydberg excited state. So, my second state is an Rydberg excited state, and this is actually an S type Rydberg excited state. If you see this lobe here, it's if you increase the thing a little bit, it's actually an S type of Rydberg state. Rydberg state generally requires a very large basis set to properly model them. Of course, in this case we are, remember we have used 6311 plus G. So, we have proper diffuse basis set. Sometimes this much diffuse basis set is not good enough, you need to go for even larger basis set, but fortunately that is not the case here. Look at the third state, it is 7A to 11A is the dominant transition. So, it is LUMO plus 3, 7 we have already seen, that is unbonding. So, this is LUMO plus 1, LUMO plus 2, LUMO plus 3. And here also if I reduce the zoom a little bit, this is also a Rydberg kind of a state, but this is a P kind of a Rydberg state. And here also it will require much more basis set. The fourth state, the dominant transition is LUMO plus from HOMO minus 1 to LUMO plus 2. LUMO plus 2 I know that it is Rydberg. Let us see HOMO minus 1. So, this you can see the node is along the plane of the bond. So, this is a what is called a nice pi orbital. So, this is a pi to Rydberg excited state. So, this is the nature of all the 4 state is. Now, one problem in this particular case is that if I look at the let us say 4th state. Now, this is very difficult to guess which is the dominant transition, because all 4 of them actually has quite big contribution. So, and that is even is the case in this, at least here it is 2. Here there are 4 orbitals which has dominant transition. So, how I will interpret this kind of state? And sometimes it is not easier to interpret a transition in the form of its a canonical molecular orbital, and you need to use different orbitals for doing this kind of things. And for that we need to go to what is called a natural transition orbitals. So, natural transition orbitals are obtained from singular value decomposition of the grounds to excited state transition density, and this can be performed like following. I think this is not very well observable, but let us do the calculation. So, you can do the natural transition orbital by giving the keyword do NTO true in your calculation. So, let us go to the H2CO example. Let me close the ChemCraft for the time being. Let me save it again and rerun the calculation. Remember what is the keyword I use? Do NTO true. Because it has read the previous Hartree-Fock steps, so the calculation finished so quickly. So, this is now generated, these .NTO files, we will come into that what they are. Let us reopen the output file again. So, these parts are all similar. I think the only thing which has changed due to the NTO calculation is after your excited state calculations are done, what it will do is that it will calculate this natural transition orbital. So, that will like the singular value decomposition for the transition density matrix for each state. So, NTOs will be calculated for each state, and for each state you will get a separate .NTO file, and that is why these are you get so many of this 2, 3, 4 kind of this. So, up to 10 because I have given 10 routes. So, you see, and each of these NTO file contains the natural transition orbital which depicts the corresponding which best depicts the corresponding excitation. So, this is for state 2, state 3, state 4. Now, just think of our original calculation. So, for state 4 there are 4 dominant contributions, whereas if I now look at state 4, it has reduced to only 2 dominant contributions, rest of the contributions are very small. So, one is from 7 to 8 and second is 6 to 9. Remember this 7, 6, 8, 9, they does not correspond to my original molecular orbital. They are new set of orbitals and we need to visualize them now. And how to visualize them? By using the tool Orca plot. So, by using Orca plot, we will generate the cube files and then we will look into it to see how they actually look like. So, I will do Orca plot. I need it for the H2CO.NTO and I will give it -I for the interactive mode. The plot type is molecular orbital plot, but if you really want you can. So, NTOs are like molecular orbital. So, I will give a molecular orbital plot and then number of orbital to plot. I go to the, I have to now give the MO number. So, I need to plot 6, 7, 8 and 9. So, let me plot first 6. So, now it will plot 6, I will generate the plot. I now need to change the number. I will again generate the plot for 7. I will again go to 2. I put the number 8 orbital, generate it, and I will again go to the number of orbital to plot by giving option 2. Now, I will plot orbital 9, I will generate the plot. Make sure that all the cube files are generated. In this case, the A means alpha, but I am working on a closed shell molecule. So, alpha and beta should not matter. Now, I can exit the program. Now, let us see the transitions again. So, first one is 7 to 8. So, this is of course a pi orbital. Let us see the 8. So, it is a nice n pi. So, this is a pi orbital. So, this is an non-bonding to pi type of orbital. This is one transition and we need to see the other transition also, and that is 6 to 9. Yes, this is 6 to 9. Sorry, this is I told it wrong. So, this is a pi to pi star transition. The one of the transition is pi to pi star, not non-bonding. This is pi to pi star transition, and the other one is from 6 to 8. Sorry, 6 to 9. So, this is the other transition from this is that orbital from the excitation is happening, and so nothing is visible. It's because if you do not see the orbital, that essentially means that you have to reduce the exponent. I think I have reduced it too much. So, this is a Rydberg orbital. So, this kind of transition is dominated by one valence excitation and one Rydberg excitation. So, this is a mixture of the two state, and in many of the cases you can get state which are neither valence or Rydberg, they are generally mixture of the two. This is how you can analyze them using natural transition orbitals. Let me close all the chemcrafts. So, this is we have done it for, and you can see that this is for S4 because all these cube files actually have the S4 index. So, this is for state 4. If I would have wanted to do it for any other state, I could have done it. You can also play if you like. It's sometimes very interesting to see which orbitals these excitations are happening from. Now, if I go back to my original pictures, okay, I can get the excited state, I can interpret them, but if I look the values with comparison to the experiment, the values are very well off, because remember the CIS does not contain any exchange of any correlation, and you need to put the correlation effect there, and that you can do using the DFT method, TD-DFT calculation. So, in case of doing a TD-DFT calculation, we are going to use the keyword percentage TD-DFT. It is like the percentage CIS only. In place of giving CIS en route 10, you get percentage TD-DFT 10. You can also give the NTO option available here. So, why we are using Chem-Bethrelib? Because Chem-Bethrelib is one of these. Remember what Chem-Bethrelib was? It was one of these long range corrected functional. What happens in the long range corrected functional? I separate the exchange into two parts. The short range part is given by the DFT exchange, and the long range part actually mimics the Hartree-Fock exchange. So, I put this range separation parameter, and this range separation parameters actually gives you pretty good accuracy for excited state, and Chem-Bethrelib is generally a method of choice for performing excited state calculation. So, now let us perform an excited state calculation. So, let me use the H2CO input file and save as. So, in place of RHF, I write Chem-B3 In place of CIS, I have to write TD-DFT true. I do not need the NTU for the time being, because I already have done the interpretation. I keep the use symmetry. I need to save as H2CO Chem-B3 Orca H2CO. I should increase the zoom. So, the TDFT calculation takes almost similar time of CIS, slightly higher. So, now let us look at the state. It is not always the case that the order of the excited state in the CIS method and the DFT methods will be same, but in this particular case they are same. First one is A2, there are two B2s and then A1, and now let us see the values. So, it was 4.57 to 383 was the experiment. In this case it is 3.958. The question is that how many digits I should write. Because my experiment has given 3.83, there is no point in writing higher digits, so I write 3.96. For the second state is 6.94. For the third state is 7.89. Actually it is. For the fourth state is 7.97. So, you see, using Cambridge relief we actually get very good agreement with the experiment. Now, this is a case where you get the very good agreement. There will be cases where the agreements are not so good, and problem is that in this case there is no systematic way to improve it. Even if I increase the basis set, it may not give you better answer, and there is no way I can make these numbers looks better. So, that actually is a problem with TD DFT.